So today we're going to start introducing finite fields. Okay. So let's start with the formal definition of the finite field. There is a certain type of finite field. So we say that for some p, okay, we'll define fp first of all to be the set 0, 1, 2, p minus 1. Okay, so we've got p elements. They're all integers, and then we will take the mapping. You should remember, say that this mapping right, and we will define it as follows. So you remember that, but by the way, I mean, we actually this is sort of like an outcome, but we'll already say that P has to be prime. P is prime. Okay, because we know that if P is prime, then Z over P is a field. Okay, but we showed it last time, remember? Because it actually followed from, I mean, we proved this. We had to prove that, that this needs to be an integral domain. Right? You can go back to previous lectures and see why, like the quotient group of Z over this ideal that is with P prime is actually a field. Okay, so this mapping, right, we actually use it to transfer the properties of this field to this set. Okay, that's all we're doing. And then we say that once we induce the structure of Z over P to Fp, then we call Fp, right, is a finite field, and we usually call it the Galois field. Okay, of order P. Okay, and this is a finite field, and how actually this looks. So actually the mapping would be, we remember that elements from Z over P, right, were cosets, remember? And then we simply map them to elements of Fp, okay? And everything becomes in Fp modulo P, right? So we use, right, we use modulo P. Okay. So actually, I mean, if we think about it, right, what do we get? We get that phi of A. Right. Actually, from here we see that phi of A is actually A. Right. That's basically what the mapping is, right? But then we get that phi of A plus B, right, is equal phi of, sorry, A plus phi of B and also multiplication follows times B equals phi of A times phi of B. Too many parentheses. And that's it. Okay, so we've got a final finite field of order P. When we talk about, and note that, I mean, we will see this later on, not so much today, but we could talk about finite fields of prime, what's called characteristic, or prime order, which we will touch in a sec. We could also look at extension fields of this prime field, but we're not going to do it today. Okay, so today is going to be focused at prime fields. And now we want to talk about the characteristic of a field. Okay, so, or actually the characteristic is wider than a field. So if we talk about, so there are a few ways to actually define this, but if we talk about an arbitrary ring, okay, I, and it doesn't have to have anything special, okay, we can talk about something called the characteristic of I, which is typically marked like this, okay, and actually so the way that we define this, and this is maybe a bit of a tricky definition, and then I'll show what happens when R actually has an identity, and then we can have a much simpler definition. But if we look at NR equals 0, okay, for any R that belongs to R. Okay? And we actually take the minimal n that satisfies this for all R in R. Okay? Then that's the characteristic. Okay? So I guess we could write it as like R mean n or something like that. Okay? But the characteristic has to bring every element of R. It's actually like the number of times that we need to add any element to itself to get to the additive identity of R. Okay, that's the definition of characteristic. And if we have not an arbitrary R, but R with identity, that I'll remind you that we usually call the identity 1, right? Because identity is always the multiplicative identity, because the 0 identity is obviously part of the ring. Then all we need to do is say like n times 1 equals 0. So how many times do I need to add 1 to itself to get to 0? Okay. Or 1 here is not necessarily the integer 1, it's the identity, right? So like, I mean, maybe it would make more sense to write it like that, right? Is like the multiplicative identity. And then if I want to look at examples, so like if I look at F2, and obviously the fields always have an identity, right? So we use the simpler definition. So char of F2 is 2, and actually, generally speaking, char of Fp is P. Okay, and if you think about it, even though we're not going to really touch it, but if because we will see it later on, but what would be the char of? And I guess it's a bit of a not a fair question, but if we have an extension field that we haven't even introduced yet, what would be the char of an extension field? It would still be P, okay? And it comes from really what is the definition of P, right? Because usually in an extension field, I mean, always the definition of P would be like, it's sort of like a vector, it would be like 0, 0, 0, 0, 1, right? Then if you add P times, you get to 0, meaning that you still will have P as a characteristic, okay? Okay, now.
I'm not, okay, I
Go on.
was tempted to jump ahead, but
No, say,
it's
whatever
like,
you can say. If it's too much, then I'll just...
So when you, in Grad 16 of like whatever curves in zero knowledge protocols, when you use elliptic curves, you see that G1 is an FP and G2 is an FP square.
They have the same characteristic.
Same order. Also,
Yeah.
the group have the same order.
Right, they have the same, not order, characteristic, okay?
Yeah.
Order is usually the number of elements, but it has the same characteristic, okay? Actually, in the generally speaking, this would be called like, again, like this is stuff that we'll speak about later on, but essentially like the base field of all these extensions, they would be called the prime subfield, okay? And all the extensions have the same order of the prime subfield, okay? That's how it works. And it actually, like, it means something about the very basic structure that these fields can actually relate in some way. All right, one thing, characteristic, and this is just a definition. So, for example, if I ask you, what is the characteristic of Z? Okay. What is the characteristic of Z, for example? Z is a ring, right? So anything that basically you cannot bound, right? Like N is basically, there's no N that satisfies it. We define the characteristic, and this is just a definition as zero. Okay. I mean, it's a little bit confusing. I would be intuitively tempted to say that the characteristic is maybe infinity, but it's probably the same, okay? Because it's like everything folds onto a circle, right? So, okay. And we usually, we say that either you have zero characteristic or you have a positive characteristic, right? And those are like two distinctly, somewhat different things.
But can't you say that zero is a characteristic of every ring?
No. Zero is the characteristic of basically any time that you cannot define, there's no finite n that satisfies, for example, n times 1 equals 0, like in Z.
But zero times anything is zero.
Yeah, but we're not, no, but 0 doesn't count. No, we don't have that,
So if we have a characteristic and it's not zero.
No, you do have, look, no, wait, okay, so let's just write it down. We said that we've got Ni equals 0, right? And we said R in I, right? So yeah, sure, plug in 0. Okay, so you've got n times, let's say n0 times 0 equals 0, so you can have anything here, right? n1 times 1 equals 0.
But if n is 0, then it's always correct.
No, it's not, because if for example, if I just check these two, okay, and here I could go with n0 is anything, okay, and here anything, and here say that n1 equals p, okay, or whatever.
So why not
something? Because I would take the minimal one that satisfies everything. It's got to satisfy all these equations. So p satisfies both.
You didn't say minimal.
Huh?
Minimal is part of the definition.
Yeah, minimal and not 0 that satisfies everything. Okay. Like it's only if you don't have anything. Yeah, if you don't have anyone that satisfies, then you go for 0. And actually, maybe that's the reason, because obviously 0 times anything is still 0, right? So maybe that's why it was defined as 0, right? But 0 is not the characteristic unless you have nothing else that satisfies.
I think this is not really a time operator because it's not the ring multiplication, right?
It's more like an
it's
addition.
n time addition, ring
Yeah,
addition.
it's addition.
Yeah.
It's addition n times.
So it's,
Yeah.
you're basically taking r plus r n times, and you're asking what's the minimal
You're right.
and
You're right.
Yeah.
You're right. You're right. That's, yeah, I guess that's a good way of stating it. Okay. Thank you. All right. So let's look at this theorem about the characteristics. So let's take a ring, okay? Take a ring that is not the trivial ring, okay? We can always, like, a lot of this stuff doesn't work well with the trivial ring. With characteristic larger than 0.
Yeah.
With characteristic larger than 0, okay? With identity, and no 0 divisors. Okay? Let's just call it this. Okay. And notice that this is nearly an integral domain, but we actually didn't require commutation, right? So we actually don't need it for this. So we say that if we've got a non-trivial ring with characteristic larger than 0, ring with identity and no 0 divisors, then characteristic of R is prime. Okay, so it's always going to be a prime thing, prime integer. Okay, and we're going to prove it. Okay. So how do we prove it? We say the following. Okay, so first of all, let's just notice that R has non-zero elements, right? Because it's not the trivial ring. So if it has non-zero elements, it means that definitely n has to be larger than 2, because n1 doesn't work. So n has to be at least 2. Okay. Now let's assume that we'll call the characteristic n. Sorry, I didn't say it. Let's just say this. Okay. Okay. So let's imagine that n is not prime. Okay. Now, if n is not prime, then we could write n as k times m, whatever, some factorization of n. Okay. Now, and obviously, right, k and m are between 1 and n. Okay. Now, let's do the following. Let's say that 0 equals n times e, right? So that's by definition, if n is the characteristic. Right, now we'll break it up so we can say that it's actually k times e times n times e, right? Okay, yeah, I'm whatever, like I'm using like distribution and whatever, like I'm just skipping a few steps. So if that's true, then either k e equals 0 or m e equals 0. Okay, and we'll just arbitrarily choose that because it has no 0 divisors, right? And by the way, it's n times e because of identity. You see why we need these conditions, okay? Now, let's just assume without loss of generality that KE equals 0, okay? Right? Now, if KE equals 0, I mean, it suffices to use the previous definition, right? But then the characteristic is less than n, right? So then, whatever, like, we found that characteristic of R is less than n. So then n can't be the characteristic, right? And we notice that the only time that we're not going to get this is if n is prime, right? Because then it doesn't have a factorization, apart from like trivial factorizations, right? Okay. So continue with the same idea, right? Now we'll do another theorem that's related, and we will say that a finite field, right? So car of, I'll call it whatever, car of f finite, okay? I mean, it's sort of like we're going in circles a little bit, is always prime. So actually all we need to show is that for a finite field the characteristic is always positive, right? Because we showed that if it's positive then it's prime. So let's show that the characteristic of a finite field is positive. So since we've got just a finite number of elements, right? We've actually got, whatever, let's just assume that we've got the elements are, right, so say n minus 1. All right, so now let's choose the following. Let's say that we've got k, okay, and k is between n and 1. Actually, let's take k even between 1 and n, not including, like n minus 1, okay? And then let's take some m that's greater than or equal to n, okay? And we take them both. We take them both such that KE is equal to ME, right? And that's possible, right? We can find such relation because everything's finite here, right? And then if this happens, right, then we get that, we can do it both ways, but we get that M minus K times E equals 0, okay? So because this is not 0, right, that means that it's a positive characteristic. Okay. And that's all we really want to show. We want to show that really the positive characteristic is finite. Okay. Once there exists a number not 0 that times E equals 0, right? It's a bit confusing, but all I want to show is that n minus k is not 0. Okay. If n minus k is not 0, then the characteristic is not 0, right? Because there exists something.
Okay.
Okay?
Okay. So why is it prime?
Hmm?
So why?
Oh, it's prime because of the previous theorem. we said that if a ring has a positive characteristic, right? And if it's got an identity and no zero divisors, then the characteristic has to be prime. Right? So it follows from the previous theorem. Okay, and I mean, I'm not going to give examples here because I think that the examples are pretty simple, right? You know them. Okay. It's going to be a quick session today. Either because everything is simple or because you're quiet. So I've got one more. I've actually got one
Get your
more.
guns out.
Huh?
I'm telling him to bring take his
that is-
ammunition out.
Yes. Okay. Last thing for today, and perhaps maybe the most interesting is what's called the freshman's theorem or freshman's exponentiation. Okay. Which I find is a pretty funny name. Oh, I see that it's spelled freshman and not
Ah.
freshman. Okay.
Oh, it's actually a name of a person?
No, it's the dream of all the freshmen, not just a
Okay.
specific one. Right? You like calling it freshman dream, right? Yes. Okay. So, all right. So we've got I, commutative ring. Okay, with prime, actually we'll write it, car of R is prime. Prime, okay, we'll actually say that's P. So actually that's all we need, okay? Now, I mean, this could connect back to, does it have an identity, doesn't it? But we're going to leave it at that, okay? So it doesn't, obviously it works for a field, okay? But maybe it could work for a slightly less restricted structure. And then we get the following, we get that A plus B. Remember that actually everything here becomes mod the characteristic, okay? But we're not going to write it explicitly. So this actually equals a to the power of p to the power of n plus b to the power of p to the power of n. And we've actually also got the, the subtraction form, which would be the same with minuses. Okay, so this also works. Okay, I could do a minus b. Okay, which is pretty cool because this could be useful. Actually, we say that A and B are in R, right? But N could be anywhere in Z. It could be any integer. Okay, and P is a characteristic, of course. Okay, so how do we prove this? Yeah. Okay, so let's start off with the binomial, right? And I'll just see. Maybe I'll write it down here. I'll try to keep this here. Okay. So let's prove something else that we'll use. Let's take the binom n over k. Okay. For any two integers. Okay. N is greater than k. Okay. So I claim the following. I claim that whatever n divides this if GCD of K and N equals 1. Okay? That's my claim. By the way, there's a lot of interesting stuff with this. Okay? With just a simple question of like what divides this binomial coefficient. Okay? It's easy to, right? I'm not going to prove it, but obviously, like it's always an integer, always a positive integer. Any ideas how I prove this?
Just open it. No.
Okay. What do
With
I
the
open it?
factorial.
Okay, so let's try and open it and let's try and identify some pattern. Okay. So I've got right n times n minus 1 times n minus 2, right, all the
You
way
can
through.
do,
What?
you can do only n times n minus 1.
Yeah, n minus 1 factorial.
Factor. Sorry. You can open just one stage, you don't need to open all the stages.
You're right. That is, yeah, okay. You're right. So you already know
Yeah.
the proof, right?
I'm guessing.
You're guessing. Okay. So what would we have here? K times K minus 1 factorial, right? And here we still have
n minus
n
k.
minus K factorial. Right?
Another question.
Okay. So now, yes. Okay. So now how do I rephrase this? What does this equal?
So we can get rid of the k minus 1.
Of this?
Yeah,
How?
with the things from above that correspond.
You get rid of things from above with this one usually, right? There's that.
That one?
But I'm asking something else. Let's
Right.
here, let's do this. I'll give you a hint. So what are we left with?
You can also take n minus k minus 1, n minus k minus
Okay.
n.
What are we left with?
So you can write it as n minus 1, k minus 1
Exactly.
multiplied by.
Okay. This is, by the way, pretty standard. I mean, we use this a lot.
Okay.
Yeah,
Okay.
so like that. So.
So, so this is an integer, okay? Greater than 0. Now, that's all we need to know, right? This is an integer greater than 0, so put that aside.
That's
And now, right, if the GCD is 1, k doesn't divide n, must divide this integer, so we have, this is a multiple event.
yeah.
Has to be, okay? Because we've got like n times something divided by k. If k divides n, then maybe it's not a multiple event, but if k doesn't divide n, then it's definitely a multiple event. Okay, so we'll use this lemma, okay? We'll use it up here, so just remember it, okay? I'm going to erase it now because I need room.
Can you just say that k divides whatever inside the brackets and then n must divide everything, no? If you write the last expression,
Yeah.
so you can say n over k
I
times,
don't care, yeah, k must divide, look,
and then n must,
essentially it has to be an integer, okay? Right? So I just
Yeah,
care that
exactly.
k doesn't divide n, so I have n as
yeah.
a factor. Okay, that's all I care about.
Yeah.
And then
Yeah.
obviously it must divide the other binomial, otherwise it won't be, the result won't be an integer, which by definition has to be an integer. Okay. All right, so let's now break up, say, the positive, the addition, okay? Let's break up the addition to like by the binomial theorem, but we'll take just a plus b to the power p, okay, at this point. And then, right, we know that it's actually equal to a to the power p plus p over 1, right, a to the p minus 1 times b, right, and then we've got all the middle terms, and then the one before last would be p minus 1, right, which is the same, but we'll write it anyway. A times b to p minus 1 plus p to the power p. Okay. So I've got all of these terms. Right, obviously here, this is like 1 and 1, that's like p over p or p over right, p over 0, which is the same, and we know that, okay, so then, now what we need to see is that really all these midterms, right, are factors of, are like, have divisor p, right, by our previous lemma, right, because p is prime. So modulo p, they all drop. Okay? And then since they all dropped, or all I'm left with are just the beginning and the end. Okay? So we've proved, we've nearly proved the first day. Okay? Now, how do I use that? Huh?
Yeah, so now you need to do p to the n.
Yeah, so let's just write that on the side here. We'll say that a plus b to the power p equals a to the power p plus b to the power p. Okay, and that we've proved, so we're gonna erase this. And now, right, I want to go to a plus b, not to the power p, but to the power p to the power n. So what can I do?
So you can use that.
How?
And then a to the p plus b to the p to the power of n. Right? Then put the
Yeah.
p inside.
That's what you meant?
Yeah, but to the power of n, but p is a to the p and b to the p.
Like that? That's like if I'm starting to break it up, then that's how I would break it, and then I know these, right?
Why did you break it? It's p to the n, it's not to the power. Okay.
P to the power. Right, and that is actually all to the power of p to the n minus 1. So we can start again, and actually you can just prove it by induction.
Yeah.
Okay.
What?
Right, because you can just say a to the p and b to the p are some other constants, right? They're like, so we're like a
Okay.
tilde plus b tilde to the power of p n minus 1. Eventually, because n is finite, you get the same thing, right? Okay. So the recursion continues as much as you want. Okay.
So the minus thing works only if p is not 2, right? If p equals 2, then it will still be, like even if there's a minus on the left hand side, it will still be a plus on the right hand side.
Oh, you mean like F2? Yeah, okay. Yeah. Because for F2, minus and plus is the same.
Yeah, but it's not just f2, it's everything with a characteristic 2.
Right, no, I agree. Yeah.
So
Anything with p equals 2, you're right. F2, yeah. Okay.
It's a minus only because it's odd and not even.
Where? What's a minus?
The minus on
On the right hand
the
side.
right hand side.
If you do
On
a
the right.
minus b, you get a minus b.
Yeah, only because p is odd.
Only because?
P is odd.
Well, I guess P can't be prime and even unless it's 2.
Yeah.
Okay. Yeah.
The important thing is
Okay. I don't know. I didn't try and think specifically of that, but I guess so. But let's see. I mean, it's easy to get to show that the minus works just by simple manipulation. Okay. And actually, what we do is we say the following. Okay. We say that a to the power p to the power n. Okay. And now we're just going to manipulate it. Okay, and say that it's a minus b plus b all to the power of p to the power n. Okay, so I've done nothing.
Can't you just substitute minus b with the plus c?
I guess maybe you can. Yeah. Yeah. Yeah.
but how
And then yeah. I guess you would be able to. Yeah, and then you get the like odd minus summing that was mentioned before. Okay, I guess this is the same. Okay, but I'll continue with this just because. So now, right, we break it up, and I think that maybe this is like more formally the way to do it. So now we use the theorem, right? And until here, this is just basic manipulation. Now we use the theorem. What do we get? We get a minus b to the power b to the power n plus b to the power b to the power n. And now if we rearrange things, we get exactly this. Okay. So yeah. And that's all I've got for you for today. Okay.
Thank you very much.